Section 6.1, exponential functions. In this section, you're going to evaluate exponential functions, find equations of exponential function, use compound interest formula, evaluate exponential functions with base E. In this unit, we will explore exponential functions, which can be used for modeling growth patterns such as those found in bacteria. We will also investigate logarithmic functions, which are related to exponential functions. Both types of functions have numerous real-world applications. For example, India is the second most populous country in the world, with a population of about 1.25 billion people in 2013. The population is growing at a rate of about 1.2% each year. If this rate continues, the population of India will exceed China's population by the year of 2031. When populations grow rapidly, we often say that the growth is exponential, meaning that something is growing very rapidly. When exploring linear growth, we observe the constant rate of change, a constant number by which the output increases for each unit increase in the input. The scenario in the India population example is different because we have a percent change per unit time, rather than a constant change in the number of people. Before we dive into section 6.1 and explore exponential functions more, let's do some warm-up activities. First question here, or first skill that you need to refresh, is how to simplify these expressions and how to deal with exponents. So when we have the same exponents for the first one, we have to keep the same base. When we have the same base for the first one, for the first example here, notice how we have the same base. So in order to answer that question, we're going to keep the same base and add the exponents together. So it's going to be x to the 2 plus 3 is 5. If you're dividing b, then you have the same base. You're going to subtract the exponents. So it's going to be x to the 7 minus 3, which is 4. C, if you have an exponent raised to a power, then you're going to multiply these powers together. So it's going to be x to the 3 times 2 is 6. If you have a negative power, then you can basically write it as the reciprocal of that number to turn the exponent into a positive. So it's going to be 1 over 5 to the second, which is 1 over 25. And if you have a power, you have to distribute that over the numerator and denominator if you have a fraction. And then, since it's negative, it's going to be 1 to the negative 2 over 4 to the negative 2. And then you take the reciprocal and change the power into positive. So it's going to be 4 to the second over 1 to the second, which will give you 16 over 1. The second activity, you need to know how to deal with numbers that have a specific base. For example, for a and b, I would like to change that into a base of 10. I know that 100 can be written as 1 over 10 to the second power, but I want this to be of a base 10. So in order to take it up, I will take this and I'll say 10 to the negative 2 power. So I'm going to switch the power into negative and take the reciprocal of the fraction. Same with 1 over 10,000. So 1 over 10,000 is 1 over 10 to the 4th power. Again, this can be turned into 10 to the negative 4th power. Base 2. So if you have 1 over 8, 1 over 8 can be written as a base 2. That is 1 over 2 to the 3rd power. Again, we're going to bring it up, so it's going to be 2 to the negative 3. 1 over 32 is basically 1 over 2 to the 5th power, which is going to turn into 2 to the negative 5 power. Question number 3, describe the difference between f of x equals x squared and f of x equals 2 to the x power. This function right here, we studied it before. It's the parabola, which has a period where it's increasing and a period where it's decreasing. So it is increasing on negative infinity to 0, and it is decreasing on 0 to positive infinity. However, this function, if you keep applying numbers, for example, 2 to the 1st power is 2, to the 2nd is 4, and 2 to the 3rd is 8, and 2 to the 4th is 16, and etc. Notice how there is a growth always. So this function is always increasing. It's increasing from negative infinity to positive infinity. It does not have intervals on which the function is decreasing in this case. And we can confirm by graphing. So if we create the table of values for the two functions, f of x and g of x, let's name this g of x. So when x is 0, f of x will be 0, and g of x is going to be 2 to the 0 power, which is 1. When x is equal to 1, x squared will be 1, and 2 to the x power will be 2 to the first power, which is 2. When x is equal to 2, then x squared is going to be 4, and 2 to the x power is going to be 4 as well. And then when x is equal to 3, x squared will be 9, and 2 to the x power is going to be 8. If x is equal to negative 1, then x squared will be 1, and 2 to the x power is going to be 2 to the negative 1, which is 1/2. If x equals negative 2, x squared is going to be 4, and 2 to the x power is going to be 2 to the negative 2, which is 1/4. And if x is equal to negative 3, x squared will be 9, and 2 to the x power is going to be 2 to the negative 3, which is 1/8. So if we graph f of x here equals x squared, we're going to get 0 and 0, 1 and 1, 2 and 4, 3 and 9, and then we're going to get the numbers on the other side as well. So the graph is going to look something like this, and it's the famous parabola that we know. The function g of x, which is 2 to the x power, is going to be 0 and 1, and then we get 1 and 2, 2 and 4, we get 3 and 8, and then we get negative 1 and 1/2, and then negative 2 and 1/4, and then negative 3 and 1/8. So the graph of the function is going to look like this. It's going to be very close here, and then it increases, and the y-intercept is 0 and 1. And it continues growing. So that is the graph of both of these functions. Basic exponential vocabulary. Percent change refers to change based on a percent of the original amount. Exponential growth refers to an increase based on the constant multiplicative rate of change over equal increments of time. That is a percent increase. Exponential decay refers to a decrease based on a constant multiplicative rate of change over equal increments of time. That is a percent decrease. The most famous exponential function is the function f of x equals 2 to the x power. Let's define the behavior of the graph of the exponential function f of x equals 2 to the x power and highlight some of its key characteristics. Notice the first thing, that the domain of this function is all of the real numbers. The graph extends smoothly from negative infinity to positive infinity, while the range is only from 0 to positive infinity, and 0 is exclusive because there isn't a value that we can plug for the x to make 2 to the x power equals to 0. On the right side of x, the function increases without a bound, or as x approaches positive infinity, the function increases without a bound. As x approaches negative infinity, or on the left side of x, the function approaches the 0 or the x-axis, and it will never cross or touch the x-axis. And as you can see here, the function is always increasing. There isn't any interval on the domain where the function is decreasing. It's always going to be increasing. As I mentioned before, the graph of f of x will never touch the x-axis because base 2 raised to any exponent never has the result of a 0 or a negative result. You will never see a negative result, and you will never see a 0 result. The horizontal asymptote for this function is the x-axis, or the y equals to 0, the line y equals to 0, and the y-intercept is 1, or 0 and 1. So that is the y-intercept right here. These are the characteristics of this function. Now, if we study exponential functions in general, we can define exponential functions as follows. For any real number x, an exponential function is a function with the form f of x equals to a times b to the x power, such that a is a non-zero real number called the initial value. A is non-zero real number called the initial value. B is any positive real number such that b cannot be equal to 1. And this can represent growth or decay. We will learn when it's going to be growth and when it's going to be decay. And by the way, you could say that b is equal to 1 plus r, such that r is the rate of growth or decay. The domain of this function is all of the real numbers, just like the previous one. And the range of this function is all of the real numbers if a is positive. If a is negative, then the range is all of the negative real numbers. That is if a, or the initial value, is negative. The y-intercept is going to be 0 and a, which is the initial value. And the horizontal asymptote is going to be the x-axis, or the line y equals to 0. We said that the base b has to be a positive real number and not equal to 1. The reason for that is because if b is negative, we're going to run into the complications of dealing with complex numbers. But if b is positive, then the function f of x equals a to the b of x is going to be defined for all of the real numbers. So that's why b cannot be negative, because if b is negative, we're going to have to deal with complex numbers. And b has to be not equal to 1, because if it is equal to 1, then we're going to have f of x equals to a times 1 to the x power, which is basically f of x is equal to a, and that is a constant because a is a non-zero real number. So in this case, we're dealing with a constant function instead of an exponential function. We're not going to have any growth or decay if b is equal to 1. That's why b cannot be equal to 1. If the base b is greater than 1, do you think it is an exponential growth or decay? The answer is it is an exponential growth. How do I know? Because if b was bigger than 1, let's assume it's 2. The basic one is 2. Let's say a is equal to 1 and b is equal to 2. So it's bigger than 1. We have f of x equals 2 to the x power. And this function increases by the increasing of x. So for example, 2 to the first is equal to 2. 2 to the second is equal to 4. 2 to the third is equal to 8, and etc. So it grows as x increases. And then if b is less than 1, but it's positive, greater than 0, then in that case it's going to be, so this is a growth if b is bigger than 1. If b is bigger than 0 but less than 1, in this case it's going to be a decay. I know that because let's assume that b is equal to 1/2. So a is equal to 1 and b is equal to 0.5. That will lead to the function f of x equals to 0.5 to the x power, or 1/2 raised to the x power, which will lead to, when x is equal to 1, we're going to have 0.5. When x is equal to 2, we're going to have 0.25. When x is equal to 3, we're going to have 0.125. As you can see, the number is decreasing as we increase the value for x, which means in this case we have in decay. That's why we know it's a decay function. Evaluating exponential functions. For the coming examples, we need to find whether the equation represents exponential growth, decay, or neither, and evaluate each equation for the given x value. So for the first function right here, by examining the base, we can determine if the function is increasing or decreasing. So the base is 3 in this case, and the base is bigger than 1. 3 is bigger than 1, which means this is a growth. This is an exponential growth. To find f of 2, we're going to plug x is equal to 2. So we're going to have f of 2 equals to 5 times 3 raised to the 2 plus 1. And that will lead to 5 times 3 to the third power. That is 5 times 27, 135. G of x is equal to 5x squared plus 3. This is neither, because quadratic function increases and decreases, doesn't always increase or it doesn't always decrease. So we're going to say this is neither. And to find f of 2, we're going to, this is g of 2, by the way. So we're going to say g of 2 is equal to 5 times 2 squared plus 3, which will be 5 times 4 plus 3, that is 23. H of x is equal to 2 times 1/2 raised to the x plus 1. The base here is 1/2, which means it's less than. So 1/2 is less than 1, which means this is a decay based on these two rules. And in order to find h of 2, we're going to have h of 2 equals to 2 times 1 over 2 raised to the 2 plus 1, which will be 2 times 1/2 to the third power. That is 2 times 1 over 8, and that is equal to 1/4.